my part of the project, I am working on some synchronous resonances on a laboratory test bed. Alongside with me is my team member, Chanh, as well as our technical advisor, Dr. Mark Boston. Our faculty advisor is Dr. Angela Rasmussen with the support of Intermountain Power Agency, Williams, and Reliable Control. We were able to accomplish this project. So before I go into the details about the technical part of my project, I would like to first show you a photograph here of an incident, which is the Tacoma Narrows Bridge in 1940, which is collapsed only several months after its opening. This incident is caused by the structural design of the bridge, as well as the wind factor that create a resonant frequency that caused the bridge to oscillate and leads to this tragedy. In power system, we also have resonance, and more specifically, the phenomenon is called the subsynchronous resonance. And since Kellen is already going to the detail, explain how and why it is important that we need to minimize this resonance, and therefore I'm not going to explain it again in this case. And on that note, here is the flow charts of the tools, experiments, and the solution that I arrived with for my part of the project. First, I would like to talk about the tools, which consist of MATLAB Simulink, DSpace, and Power Electronics, and as well as the electric machines. And these are the DC motor, the doubly fed induction generator, or DFIG. We also use it for the wound field synchronous generator, or WFSG. The power electronics drive board, DSpace breakout box. We have the grid connection box, current sensor, parallel connection box, and a 3-phase resistor. We also use 3 line inductors and 3 series compensation capacitors, and this is for the second experiment that I will talk later in the presentation. So with the hardware accomplished, the next step is to move on to the first experiment, which is the connection of a doubly fed induction generator in parallel with the wound field synchronous generator. And this experiment is for me to observe if there are any inter-area oscillation. And the first step is to actually create or in this case, implement a Simulink model, which to adjust the parameters of the rotor voltages, as well as the motors on both of the generators voltage, as well as the feedback input that I will implement into the DC motor to give us a more of an AC characteristic. And with this, we can actually observe a better inter-area oscillation. Then, with the software complete, the next step is to connect up the hardware. And in this case, I actually show you a circuit diagram to have a better visualize of how I connect these equipment together. And with both the hardware and the software accomplished, the next step is to capture some results. And here I have an interesting result that of a DFIG feedback input of 0.002 into the motors on the DFIG side. And from what we can see here, the power of both generators are not swinging against each other like the one that we see in Kellen's experiment. And in this case, there is no inter-area oscillation that was able to observe. So the next experiment that I conducted was to connect a doubly fed induction generator to the grid through a series of compensated lines. And in this experiment, I focused on 2 compensated levels, and they are 50% and 70% compensated line. To be able to calculate these compensated levels, first we have to estimate the values of the inductors as well as the capacitors. And in order to do this, there are 2 Simulink models that was implemented. The first Simulink model you can see here is the estimation of the inductance and the resistance. And the way that we do it is to implement input a sinusoidal voltage of a frequency of 60 hertz into the inductor, and then we can use the real and reactive power to calculate the resistance and the inductance. Similarly, for the capacitance and the compensation level, the way that I actually capture this is to connect the capacitor in series with the inductor, and that will give me the total reactance. And then using the inductor value that was captured in the first Simulink model, I can input it into the computation block here, and that will give me the difference, which is the capacitance value. For the compensation level, we actually take the ratio of the reactance, the total reactance over the inductor value to give us the compensation level. And here is a D-space layout, which is to communicate between the MATLAB Simulink and of course, the D-space application. Which in this case, I show an example that I was able to capture the capacitance of 451 microfarad, which is turned out to be about 70% compensation level. And with that, I actually created a table here to show you some of the combinations of the inductors and capacitors that were used in this experiment. With 50% compensation level, the connection that was made is to connect the inductor 1 in series with capacitor 1, inductor 3 connected in series with capacitor 2, and so on. For 70%, I connected the inductor 1 in series with the capacitor 4 in parallel with C10 and so on. I also want to note that there were some of the capacitors that we bought, but turned out that the nameplate wasn't correct because, for example, on this one it's showing us that it's 200 microfarad. But when we actually implement it into our system, it's actually showing us a value of 600 microfarad, and that is very incorrect, and that's why we were not able to use these type of capacitors in our experiment. And with the capacitors and the inductors values calculated, the next step is to actually connect it with the motors and to the grid, which we can see on the circuit diagram here how I connect everything together. Then two more Simulink models were built in order to operate the machines. And the first model I show here is the open loop experiment. The reason that it is actually an open loop is because the power generated was not input back into the system, and therefore we cannot control the power of the generator. While for the closed loop experiment, we actually input back power into the system, and therefore we can actually control the generated power using Pref and Qref. And with that, here are the results for open loop experiments, which we can see the oscillations, the subsynchronous resonance for both 50 and 70% compensated line, and this is for the power. Also, for the closed loop experiment, we also capture the subsynchronous resonance in this case as well, with both the real and reactive power for 50 and 70% compensated line. And in this case, because our second experiment shows a presence of subsynchronous resonance, and therefore my solution is to focus on the second experiment, which is to design an advanced excitation controller, or AEC for short. And in this case, I actually collaborate with Hannah Biasmet, and she is a graduate student here at the University of Utah. We were able to work together and create 4 controllers. And in this case, for the experiment, controller number 4 works the best and show us the stable result. And that's why here is the result for the controller number 4 that we were able to capture for both of the 50 and 70% compensated line. And you can see that on the blue line is the power with the controller, which we can see a reduction in subsynchronous resonance, while the red line showing you without a controller, and you can see that there are quite a lot of resonance there. I also want to note that the peak there on the blue line it's actually not a glitch or a problem with our controller. It's actually because we input a reactive power into the system, and that's why it causes a little bit of a distortion in the waveform there. And on that case, for the conclusion, for the first experiment with the parallel connection of the doubly fed induction generator with the one-film synchronous generator, I was not able to capture any inter-area oscillation. While for the connection of the doubly fed induction generator to the grid through a series compensated line, we were able to capture the subsynchronous resonance. And one of the advanced excitation controllers, which is controller 4, we were able to observe that there was a reduction in the oscillation. For the overall conclusion, the parallel connection of two WFSGs in Kellen's experiments shows inter-area oscillation, while for my second experiment, the doubly fed induction generator connected in series with the compensated line shows subsynchronous resonance, and therefore the power system stabilizers and the advanced excitation controller were implemented in order to minimize these two oscillations. And there are still future improvements in order to even reduce more of this oscillation by continuing tuning the PSS and the ADC. And to wrap everything up, to reduce the amount of oscillation and some incident like this could happen in power system, we must first have to experiment, provide information as well as observe oscillation in order to create a solution that would reduce the oscillation in order to stop this kind of tragedy that happened in power system. And here are the references that I used. Thank you everyone for your time, and I would like to hand it over for any questions.
You gave the very visual example of the Tacoma Narrows Bridge. Can you give me an actual example of how subsynchronous resonance appears on a power system, and an example of that happening?
So the subsynchronous resonance could happen when we getting closer to that resonant frequency, and that is, in this case, I actually showed that it's 50% to 70%. And if we go more than 70%, we can see even more oscillation could create an unstable system as well.
Well, what's the catastrophe look like to the user?
The catastrophe is not as not really tremendous as the Kellen's case, because in this case there's actually a transmission line, so there would be a circuit breaker and stuff like that, but it would prevent any damage to the grid or to the generators. But in Kellen's case, because how two generators are swinging against each other, so that could cause a more tremendous problem.
Did you meet any real-world people that kind of deal with this on a daily basis, power companies or anything?
I wish I could. Yeah.
Or what they do in real-world applications to try to find it and keep it from happening. Essentially, maybe using your experiments.
Yeah, that just would be a great way to just kind of give them a observation of how we can reduce this oscillation from happening. Yes, sir.
If we were to give you relative positions on either end of a turbine generator shaft, could you use that input somehow in your system to detect and issue a signal that would dampen those oscillations if the shaft is torquing?
I actually, because in this case, for the controller, we actually used the stator current to be able to reduce the oscillation, and we also have the placement of the pulse, so it could, in your case, it could actually work.
So it's interesting because in the first case, he didn't show the plot, but he has these plots where he had encoders on both machines, and he could actually see the same oscillations on the position of the machine as he could see in the power. So you could see it in the power. In his example, I don't think we ever plotted it. We have that, but I don't believe there is much motion of the rotor. These are much faster frequencies. And we talk about 20 hertz here as opposed to much lower frequencies otherwise. So here I don't think we would see anything. I don't think it would help, but we haven't tried. It's possible there would be a small signal there to be seen, but it's mostly an electrical oscillations as far as I know.
Okay.
So, but we did, in the other case we looked at it, it was really interesting to see the relative movement of the shaft.
Right. Okay, thank you.
Are there any other questions? Well, thank you everyone for your time.